This conference will now be recorded.
Hello everyone. The topics that we will discuss today is balancing of redox reactions and redox reactions as the basis of titration and some related problems. Now, under balancing of redox reactions, there are basically two methods. One method is oxidation number method. So this method, we have already seen one example, that is how to balance redox reaction by using oxidation number method. But in that reaction, we have not used any acidic medium or basic medium. But suppose if we have any reaction which is occurring in presence of acidic medium or basic medium, then how to do it, that we will see today with a particular example. Now, when it is acidic medium, though it is already said in the previous class, I am again repeating it. If it is occurring at acidic medium, you can add H plus, but you cannot add HO minus. Only in basic medium we can add HO minus, and if it is acidic we can add H plus. Now this H and HO, this is basically to balance the hydrogen and oxygen both free. So if it is acidic medium, if we see that in any side there is lack of oxygen or extra oxygen, you have to balance the oxygen atom by adding required number of water molecules. So if in the left hand side there is one oxygen is less, you can add one H2O. Now when you are adding one H2O, basically you are adding two hydrogen. Now you have to balance these two hydrogen in the other side. And how you can do so? You can do so by adding H plus ion, because it is occurring in acidic medium. Now this is for acidic medium reaction, but if it is in basic medium, then what to do? Now the same method you have to do if it is basic medium. Same thing. First balance the atoms as it is done in acidic medium. Now as you have added H plus to balance hydrogen, obviously it is basic medium, so H plus you have to neutralize. How you do so? Now after balancing H hydrogen atom in terms of H plus, now you have to add equal number of hydroxide ion both sides, so that this H plus and HO minus together can form water molecules. Fine. So we will solve one such problem. So see here we have this reaction, permanganate ion plus bromide ion, and then there is formation of manganese oxide, MnO, and BrO3 minus bromate. So we have to balance this in base, keeping in mind that this reaction is occurring in basic medium. So obviously we can add H2O or HO minus, but not H plus. Now when it is oxidation number method, first thing that you have to do, just find out the oxidation number. So here it is +7. We have done it several times for MnO4 minus. Now the next species is it is already having the charge -1. Then for MnO2 it is +4, because we have two oxygen, each oxygen -2, so total positive charge over Mn is +4. What about BrO3? BrO3 is basically, this is an extra negative charge. Now 3 oxygen, so for each oxygen it is -6, so it must be +5. So +5, total negative charge -6, excess negative charge, overall charge is -1, BrO3 minus. So here if you see MnO4 minus, here manganese, its oxidation number is changed from 7 to 4. That means it is 4 minus, that is if we subtract it, it is basically gain of electron, right? So when it is gain of electron, I am writing here +3. And in terms of Br minus, from -1, now it is +5, right? So it is basically -6. Now as it is -6 and this is +3, next step what we will do, we will multiply number in such a way so that the total charge becomes same. So now it is +6 and this is already -6. So these two are balanced. So as we have added, multiplied 2 in case of Mn species, now I will write the equation like this: 2 MnO4 minus Br minus, then 2 MnO2. So both sides now you can see number of manganese, it is same, it is both 2. So it is okay. Now if we check oxygen, total number of oxygen in the left hand side 4 into 2, it is 8. But in the right hand side, it is 2 into 2 and 3. That means 7. So we have to add 1 water molecule to balance oxygen. As you have added 1 water molecule, 2 H plus you have to add here so that hydrogen number is same. But this is basic medium. So to balance this H plus, what we are doing, we are also adding hydroxide, but that you have to do both sides. Now these two together, it will make 2H2. So finally, if you write this equation, it will be 2MnO4 minus plus Br minus plus 2 water molecule. Here it is 1 water molecule, so it will be ultimately 1 water molecule only. Then 2MnO2. Bromine is already same both sides. And 2HO minus. So this is the final balanced equation. 2MnO4 minus plus Br minus plus 1 water molecule. In the right hand side, 2MnO2, BrO3 minus 2 hydroxide ion. Okay, so we have solved it in basic medium and also in oxidation number method. Now the next method is ion-electron method. So in this method, mostly it is applied for ionic type of redox reactions. But the reaction that you are seeing here, it is not ionic. It is given in terms of neutral equation, that is molecular equation. So if it is directly given in the ionic form, it is fine. But suppose some equation is given and it is asked to balance it in terms of ion electron method. First, you have to write it in the ionic form. Okay. But before doing so, the first step what you can do, okay, first you have to write the ionic form. Then you assign the oxidation number, or you can also assign the oxidation number first. So see here, if you remove potassium from KMnO4, it will be MnO4 minus, then FeSO4, ferrous sulfate, and here it is ferric sulfate. So what is the difference? Sulfate ion is same, but formula is different. So here it is basically iron 2 plus, here it is iron 3 plus. Now sulfate ion both side, it is basically spectator ion, there is no change. See, sulfate ion, it is same both side. So sulfate ion we can cancel from both side. We are writing only the species where there is change in some oxidation number. Okay. Then we have H2SO4. That means this reaction is occurring in acidic medium. Now when it is acidic medium, you can write H plus. You can also write 2H plus or H plus. It doesn't matter because ultimately we will balance it. Then right hand side we have MnSO4, but SO4 we are cancelling because there is no change in the SO4 unit. It is simply Mn2 plus. How it is Mn2 plus? If you remove SO4, which is carrying total 2 negative charge, remaining positive charge over Mn is 2 plus. Now iron 3 plus. Okay. Then we have potassium ion, but potassium ion is both side potassium plus. So again it is spectator. We are not writing it, and water molecule. Fine. Even if you do not write it, it is okay because ultimately after balancing it will be fine. So write the ionic form of this and assign oxidation number. So we have already written some of its oxidation number, but here it is not written. It is +7. For iron it is 2 plus. Then right hand side it's already written. Now as it is ion electron method, it is also called half reaction method. So we will break this equation into half reaction. One reaction will be oxidation, another one is reduction. Now if you look at this equation carefully, you will see Fe2 plus, it is oxidized. That means Fe2 plus, its fate is now Fe3 plus. Now to balance the charge, what we will do, we will write electron, or you can also do it later, but I am just writing it here. What I am doing, see here 2 positive charge, but in the right hand side it is 3 positive charge. So I am just adding 1 electron. 1 electron is removed from Fe2. Now the other part is MnO4 minus with +7 oxidation state. H plus medium and Mn 2 plus. Basically here if you do not write H plus then also it is okay, because ultimately we know it is in acidic medium, so we can also make up it later. So if we look at this separate equation, this equation is basically reduction, because from plus 7 it is converted to 2 plus. It is gain of electron. You can also write electron here, but we'll do it later. Why I'm saying I'm not writing the electron here, because we have to also add correct number of H plus, and H is also carrying some positive charge. So once we are done with balancing of hydrogen and oxygen, then it is better finally you add electron. Here I have directly added the electron because here we do not have any H or oxygen, but in this case we have H, so that is why we can add electron later. So ultimately this is reduction reaction and this is oxidation. So two separate reactions we have written, right? The next step is balance the atoms other than oxygen and hydrogen in each half reaction individually. Now Fe to Fe3 plus, there is actually no oxygen involved and no hydrogen involved. But if you look at MnO4 minus, there is basically total 4 oxygen. So total 4 oxygen in the left hand side, but here we do not have any oxygen. So what I will do, I will write 4 water molecule so that oxygen is balanced. But when I have added 4 water, I am basically adding 8 hydrogen. So here I will write 8H plus. Now you can write the total number of electron, because now you know what is the extra charge in any site. So here we have -1 charge and 8H plus. That means total positive charge here is 7 plus 7. And in the left hand side, it is total positive charge is 2 plus. So plus 7, 2 plus. To balance it, we have to write 5 electrons. So now you can see the two half reactions with proper charge and proper number of electrons. So balance the atoms other than oxygen and hydrogen in each half reaction individually, but that is already balanced. Except oxygen and hydrogen, both sides equal number of Mn, equal number of Fe. So balance oxygen and hydrogen in each half reaction individually and check whether charges are same on both sides of the two equations. But we have already done it. So I am writing it again. MnO4 minus 8H plus 5 electron, then Mn2 plus 4 water molecule. And the other reaction is Fe2 plus Fe3 plus 1 electron. Now if you look at this reaction carefully, next thing basically you have to make this electron number same, so that when you add these two equations, electron will be cancelled. So here 5 electron, here only 1 electron. So this second equation, I will multiply it with 5. First equation as if you are multiplying it with 1. In this case, you are not basically multiplying anything, but in some cases, it may be that you are multiplying here 5, and another reaction you are multiplying some other number, 3, 2, 4 like this. In this case, we are not doing anything. So once you multiply like this, it will be 5 Fe2 plus, 5 Fe3 plus, and 5 electron. And when you are adding these two equations, suppose this is equation number 1, this is 2, this electron will be cancelled from both sides. So equate both half reactions in such a way that the number of electrons lost in the oxidation reaction is equal to the number of electrons gained in the reduction reaction. So here the same thing we are doing. Here the number of electron lost is 5 electron, and that number of electron gained in the reduction. This is reduction, this is oxidation. Now when you add these two equations, this is equation number 2, this is equation number 1, electron cancelled, 5 Fe2 plus, 5 Fe3 plus. So this is the final balanced equation. 5 Fe2 plus MnO4 minus, then 8H plus 5Fe3 plus Mn2 plus 4H2. There is basically no change here. Only change you can see in the other equation, that is in iron and iron equation. Fine. Now this is basically mostly it will be asked to solve it in terms of I mean to say ionic form, but you can also now balance it. That is, you can put the spectator as, remember in the previous slide, the spectator as, that is KMnO4, FeSO4, H2SO4. So that you can do here. So here if you add SO4, it will be 5FeSO4. It will be KMnO4, 8H plus. How you can write it? You can write it as 4H2SO4. Though mostly it is done in ionic form, but still for extra information, I'm just saying that if we convert the ionic equation to molecular equation, how it will change. Then Mn you have to write in terms of MnSO4, and then you have to write this potassium that you have added here. You have to write K2SO4. So like this, you can also write the molecular equation, the corresponding molecular equation. So this is ion-electron method. So in this method is specially for better for ionic equations. Now remember, in the oxidation number method, this equation we have already solved, right? We have already done it in today's class, and this reaction is also ionic. Now we have already done it by oxidation number method, but what if we done it in the method that we have just finished, which is this half reaction method or ion electron method? That also we can do. So here first we have to break these two equations in individually. MnO4 minus, it is converted to Mn2 plus. One thing you can remember, permanganate, when it is acidic medium, it is converted to Mn2 plus, but when it is basic medium, it is MnO2. That is the final product. So MnO2, this is one reaction where basically reduction is occurring. Another equation is Br minus, that is converted to BrO3 minus. Even if you do not write oxidation number, that actually for your convenience, so that you can understand which species is oxidized, which one is reduced. So these are the two half reaction. Next thing what we will do, we will balance the oxygen and hydrogen. So MnO4 minus and MnO2. So two oxygens we have to write extra in the form of water. Now when you have done so, basically you also have to write 4H plus. But this is in basic medium. So to neutralize it, I am adding 4HO minus both sides. Now these two together, it will be 4 water. So ultimately the equation will be MnO4 minus 4 water, 2 water other side. So ultimately it is 2 water, MnO2, 4HO minus. Now here total negative charge in the right hand side is total 4 negative, but single negative in the left. So here I will write 3 electrons. And as it is reduction, so you will always see electrons are on the left hand side, as if MnO4 minus is gaining this electron and it is converted to MnO2. So this is one equation. Other part, first balance the oxygen, BrO3 minus. So you have to write 3 water. Now when you have added 3 water, you have to write 6H plus. To balance H plus, as it is basic medium, 6HO minus both sides. Now finally, how it will change? These two together, 6 water. Six water, 3 water, so ultimately it is 3 water. Next is, if you look at the charge, total negative charge in the left hand side 7, but here it is only 1. So I will write 6 electrons. Now if you look at these two reactions individually, this is reduction, this is oxidation. Here 3 electron, so I will multiply this equation with 2 so that total number of electrons becomes 6. So after multiplying it with 2, it will be 2 MnO4 minus 4 H2O, then 6 electron, 2 MnO2, 4 HO. And the other equation, that is the bromine equation, Br minus, there is no change because we have not multiplied anything. So finally 2 MnO4 minus Br minus 6 HO, 4 HO. So it will be 6, 4 water, Br3 minus 1 water molecule. Sorry, this side. It is 8 because here it is 4. So 8 HO minus 6 HO minus. This is 6, this is 8. So this is the final balanced equation. So it will be ultimately the same final balanced equation as we have already obtained in case of oxidation number method, but now we have done it in terms of ion-electron method. So now it's up to you. The more you will practice, you will yourself understand. If it is not specifically mentioned which method we have to follow, then you can do it according to your confidence, which you are thinking is better. Fine. Next, we have a problem. The reaction of sulfur in alkaline medium is given below. Here it is asking the value of A. So the equation that you are seeing here, some numbers are basically missing. Here A number of, that is the coefficient of hydroxide ion, then coefficient of sulfide ion is B, coefficient of thiosulfate ion is C, coefficient of water is D, right? But it is asking only the value of A, that is what is the number of HO minus. But when you will try to know the value of A, basically you have to solve it, you have to balance it. So it is not directly asking you to balance this equation, but it is basically indirectly asking to balance it, because when you will try to find out the coefficient, you have to know the balanced equation. So the first thing that you will do, here S8, which is elemental state, 0 oxidation state. When it is S2 minus, 2 minus is directly the oxidation number because there is no other atom. Then S2O3, 2 minus. Now when it is S2O3, 2 minus, now total negative charge from, suppose it is X for sulfur, so I will write 2X. Total negative charge is 6 minus, overall charge is minus 2. So the value of X is 4 by 2, that means it is plus 2. That means this is a disproportionation type of reaction where the same species S8, it is converted to S2 minus by reduction, but it is also converted to H2O3 thiosulfate, but that is basically oxidation. So these are the two same species is undergoing reduction and oxidation. So I will write it into half equations. Okay. So first I will write S8. It is converted to S minus, 2 minus. We will balance the sulfur, it will be 8. Next step is total negative charge is 16 in the right hand side. So left hand side, it is 16 electron, and electron will always be in the left hand side because it is reduction reaction. Fine. Now the other half reaction, it is again S8 I will write, then H2O3. Now as it is H2O3, to balance the sulfur, we have to multiply it with H4. Okay. Total oxygen in the right hand side, 3 into 4, 12. That means we have to balance oxygen by writing 12H2O. But when you have written 12H2O, you have to balance hydrogen by adding 24H plus. But 24H plus, as it is basic medium, alkaline medium it is given, so you also have to neutralize it by adding 24HO minus both sides. So from this part you are getting 24 water mole. So finally what we have obtained, 24HO minus S8, 24H2O, here it is 12. So 4H2O3, 2 negative and 12H2. Now what will be the total number of electron? If we see that here total negative charge 4 into 2, that means minus 8. Here it is 24 negative charge, that means it is extra in the left hand side. So we will add 16 electron here, then only it will be same negative charge both sides. Now as we have added 16 electron, if you look at these two reaction individually, equation number 1, equation 2, both cases it is 16 electron. So when you add these two equations, number of electrons that will be cancelled. So in the final balanced equation you can write it, but directly if you see here you have 24HO minus. So is the value of A is 24? Basically it is not, because when you add these two equations, everything will be doubled. Okay, let me add it. If we add it, it will be S8. Here also it is S8, so 2S8. Then 24HO minus. Then 8 sulfide ion. Then we have 4 H2O3, 2 negative, 12 H2. So 3 species right hand side, 2 species left hand side. Now see, you can easily divide both sides by 2. Now it will reduce to S8, 12HO minus, 4 sulfide, 2 H2O3 2 minus, 6 H2. So here the value of A, this is A, and that is actually our answer. But suppose if the question is asked what is the summation of A plus B plus C plus D, then it is B, this is C, this is D. Okay, so at a first glance if you directly do not add it, it seems as if A value is 24, but actually it is 12, because here it is easily you can divide both sides by 2. So here our answer is the value of A, it is 12. For the reaction, here we have one reaction given, I minus, then chlorate ion, ClO3 minus, then H2SO. That means the reaction is happening in acidic medium. What the products? Chloride ion product, HSO4 minus, and iodine, free iodine. The correct statements in the balanced equation is or are. So it may be more than one option correct among A, B, C, and D. So it is, look at the options. Stoichiometric coefficient of HSO4, it is saying that it is 6. Then iodine is oxidized, sulfur is reduced, and water is one of the product. Basically, if you want to know whether they are correct or not, you have to balance it. Otherwise, we will not be able to answer all these statements whether they are correct or not. Because correct statements all are related to balanced equation. So I minus, if I break the equations into half, I minus is converted to iodine. -1 to 0. So this is basically Oxidation. Now it is 2 iodine right hand side, so I will write here 2. Now to balance charge, it should be 2 electron. Now the other equation, it is ClO3 minus, where chlorine is having oxidation number +5. Basically, if it is oxidation, obviously the other one will be reduction. Cl minus chloride from +5, it is converted to -1. So next we will balance the oxygen atom. Total oxygen atom, it will be 3H2O. Now as it is acidic medium, I can balance hydrogen in terms of proton. 6H plus I have written. And next step what we will do, we will see the total charge. Total charge in the left hand side, -1 plus 6, that means +5. And here it is -1. So +5 and -1, so it should be 6 electron. Then only both side charge will be -1. Okay. So see here electron is added in the left hand side because it is reduction reaction. Now if you look at these two individual equation, if you multiply this equation with 3, number of electrons, it will be equal to 6. So after multiplying, if I write the equation here, 6I minus 3I2, 6 electrons. So it is cancelled. So in the balanced equation, ClO3 minus 6 iodide, 6H plus Cl minus water, iodide. Now look at the options. The first option is saying stoichiometric coefficient of HSO4 minus. Now if you look at this species, though it is H2SO4 and HSO4 minus, but basically there is no change in the oxidation number in any of these atoms. Hydrogen it is H plus, sulfur here it is +6, here also it is +6. Only difference is one H is less. Otherwise H2SO4, if you remove one H plus, you will get HSO4 minus. So there is basically no change in oxidation state of hydrogen, of sulfur or oxygen. It is just written because the reaction is occurring in acidic medium. Now, how to know that the first statement is correct or not? It is saying that the coefficient of HSO4 is 6. Now, it is the final balanced equation that we have obtained. That is basically ionic equation. But from ionic equation also you can understand whether this statement is correct or not. 6H plus means what? If you write it in terms of H2SO4, it will be basically 3H2SO4. Now, when it is 6 hydrogen in the left hand side, obviously it will also be 6 hydrogen in the other side. It has to be because it is already balanced equation. It is not in the molecular form, it is in ionic form. But total number of hydrogen, it will always be same both sides. Though it is not written in terms of HSO4 minus, but it doesn't matter. Okay. So 6H plus left hand side, so it has to be 6 hydrogen in the other side also. And so that is why it is basically true statement. Then it is saying iodine is oxidized. Basically iodine is oxidized from -1. Now it is 0. It is also true. Sulfur is reduced, but sulfur is not reduced because it is before reaction +6, after reaction is +6. There is no change in the sulfate ion itself. So that is why this statement is false. Water is one of the product. Water is not written in the equation that is given in the question, but basically water is also one of the product because in the final balanced equation we have this water molecule. So that is why this is also true. So correct options are A, B and D. Okay. So next topic is redox reactions as the basis of titration. We know there are different types of titration techniques, and among those techniques, redox titration, it is one of the type of titration. So obviously it is, when I am saying that it is redox reaction is the basis, so there will be some reduction reaction, there will be some oxidation reaction. Between the titrant and the analyte or titrant. Now, obviously, indicator we have to use. Now, this titrant and analyte titrant, these terms are basically related to titration method, not just for redox titration, it is true for any titration. So, titrant means the solution that you are using for titration, you already know its concentration. The solution whose concentration is already known, that you will call titrant, which is added to another solution for which you want to determine the concentration. And this another solution is basically analyte or titrant. Mostly we use the first term, analyte. So the solution whose concentration has to be determined. You can also easily remember it because we are doing some analysis, right? So the solution whose concentration you are analyzing, basically that is analyte. In this way you can remember it. It is one of the most common laboratory method to identify the concentrations of analytes. Now in our syllabus, there are basically total three types of main types of redox titrations we will see, though it is not limited to these three, but these are the most important here. Permanganate titration. So permanganate titration, you can understand from this term. Obviously here KMnO4 minus will be KMnO4. If you remove potassium, it will be MnO4 minus. So permanganate ion will be involved. It is a very good oxidizing agent, and its oxidation power is maximum when it is in acidic medium. Okay, so this is permanganate titration. Then we have dichromate titration. So dichromate ion is Cr2O7 2 negative. If you balance this 2 negative charge with potassium, it will be K2Cr2O7, potassium dichromate. But if you simply pronunciation that ion anion part, then it is dichromate anion. And the last type is iodometric and iodometric. So from the name it is clear that here iodine will be involved and iodide, these species will be involved. So first we will discuss permanganate, then dichromate, and then the last one. Permanganate titration. So here see it is mentioned that some sensitive indicator is required. But KMnO4 titration is such titration where you don't have to add any separate indicator. The KMnO4 color itself can act as indicator. So here, suppose we have taken analyte oxalic acid. So you are basically determining the concentration of oxalic acid. So oxalic acid here, the formula is written C2H2O4, but actually thus it is organic acid. Its structure is like this. Okay. And the titrant is basically KMnO4. That means you know the concentration of KMnO4, you do not know the concentration of oxalic acid. Here oxalic acid is obviously the reducing agent because we know KMnO4 is the oxidizing agent. It is never, remember it is never reducing agent, it is always oxidizing agent. So we will take KMnO4 in the burette, as you can see in the picture. Look at the first picture. KMnO4 you have taken in the burette. Its solution is purple color. You from the reading you can understand what is the initial volume and how much ml you have taken, and in the conical you have the oxalic acid solution. Now you are adding KMnO4 drop wise. When the first drop will be there, will be able to see some purple color. But as soon as it will react with oxalic acid, it will be converted to Mn2 plus. And once it is converted to Mn2 plus, it is basically colorless. So gradually the color will be vanished. The first drop, when it will appear in the conical, there will be some color, but as soon as it is touching the solution, the color will be gone. So in this way, V initial, that is the initial volume. So now you can see the reading is here. So this amount we have already added. Now this is the second step. Now when you will continue this process, and the final stage when you will reach, that is when the reaction is over, all the oxalic acid consumed by KMnO4, then what will happen? In the end point, there will be some pale permanent pink color. Now you can say this is excess of KMnO4. So there is no oxalic acid left. Everything is consumed. So that is why the excess KMnO4, it is showing its color, which is persistent. So this is very pale. If you have added that is extra amount, this extra should be very less, otherwise there will be error in the calculation. So it may be just one drop, it is extra, so that we can see the color is persisting. Color is persisting means the reaction is over. So we have not added any separate indicator. And remember, in acidic medium, mostly dilute H2SO4 added, oxidizing power of this anion is maximum, because when it is acidic medium, MnO4 minus is converted to Mn2 plus. When it is basic medium, it is converted to MnO2. Now, why it is better oxidizing agent? That you can understand, because it is +7, this is +2, this is +4. So in this case, it is gain of 3 electron, but here it is gain of 5 electron. So more electron gain means obviously oxidizing power is also high. So here the discussion will be only in acidic medium. So KMnO4, it is the self indicator, as the ion has specific color. So it will be reduced to the colorless Mn2 plus ion, which is called manganese ion. So that is by final, that is when the reaction is going on, the color will be vanished. And when the color is persisting, that means MnO4 minus is still there and there is no oxalic acid left to convert it to Mn2 plus. That means reaction is complete. The last drop of permanganate gives a light pink color, which indicates the end point. Fine. Now, one question may arising in your mind, that what is the fate of oxalic acid? So oxalic acid, here if I write it in ionic form, these 2H I will remove. So it will be CO2 minus, another CO2 minus, that means 2 CO2 minus, that will be converted to carbon dioxide. Okay. So C2, sorry, it's not CO2 minus, should not be written like this. It is basically C2O4 2 negative, that will be converted to 2 carbon dioxide. And here the oxidation number of carbon is +3. Why it is +3? That will be clear if you simply consider its structure. So carbon double bond O, O minus, O minus. Now there are total 3 carbon oxygen bonds. That means total positive charge over carbon will be +3. And for CC bond, we will not consider anything because it is bond between same atom. So that is why 3 carbon oxygen bonds. So oxidation number is +3. And for CO2, it is +4. So it will change its oxidation number from +3 to +4. It means what? It means it has lost electron. So that is why C2O4 minus, oxalate ion or C2O4 2 minus, that is basically the reducing agent in this case. Now if you want to balance the charge, 2 negative charge left, we will write 2 electron in the right hand side. Fine. So this is the half reaction for the oxalate part, and KMnO4, the other half reaction that we have written before. So based on this permanganate titration, here we have a problem that though you can solve this problem easily, that it is asking the reaction of oxalate with permanganate acidic number of electrons involved in producing one molecule of CO2. Now if you simply look at this half reaction, for production of one molecule of CO2, for 2 molecules of CO2, there is 2 electron, right? So for production of one molecule of CO2, how many electrons involved? That is the question. Okay. Now, the final equation that you are seeing here, But how we can reach this equation, that we will solve by first writing the half reaction that we have already written. C2O4, 2 CO2, 2 electron, right? Now for MnO4 minus, as it is in acidic medium, it will be Mn2 plus. So this half reaction, how we balance oxygen, that we have already done. So I am doing the same thing. So it will be 5 electron. Because if you balance charge, here total positive charge 2 plus, left hand side total positive charge 7 plus. So when we add 5 electron, it will be balanced. Next thing, 2 electron and 5 electron. So this equation will be multiplied by 5 and the other equation that will be multiplied by 2. Once you do so, it will be 5 C2O4, 2 negative, 10 CO2, 10 electron. And the other equation, 2 MnO4 minus, 16H plus, 10 electron, 2 Mn2 plus, 8H2. Now both equation, there is equal number of electron. So this will be cancelled. So finally we are getting 2 MnO4 minus, then 16H plus, 5 C2O4, 2 negative. Here we have 2 Mn2 plus, 10 CO2, 8 H2. Okay. Now this is the balanced ionic equation, right? Now if you want to convert it to molecular equation, it is simple. 2 MnO4 minus, that means if you add 2 potassium, it will be converted to KMnO4, right? Then 5 C2O4 2 minus, it will be 5 if you simply add hydrogen, because C2O4 2 minus, remember oxalate ion is like this. So when you add hydrogen, so here we have to add total 5 C2O4. So basically for each C2O4 it is 2 hydrogen. So total 10 H plus should be added. Then only it will be oxalate. And here also you can see 2H2O D10 dot 2H2O. Basically when it is oxalic acid like this, I am just removing the negative charge. There is water molecule of crystallization like this. So that is why per molecule of oxalic acid, there is 2 water molecules attached. In the ionic equation, I have avoided that for simplicity. But if you write the final neutral equation, molecular equation, then we have to mention it, because oxalic acid, it is always associated with this water molecule of crystallization. Now 2 Mn2 plus, to balance this Mn2 plus, there is basically sulfate ion we have to add. Per Mn 1 sulfate, that means 2 sulfate ion. Then 10 CO2, it is already neutral, and there is 8 H2. But here it is, if you see, 3 H2SO4, right? That means here 6 H plus. Now ultimately, if you balance all this hydrogen, so total 10 H plus, here it is 6 H plus, and here 10 H plus. So that we have already in the form of 16 H plus, right? And here 2 SO4 and 2 potassium we have added. So that is why when we are adding potassium, here 2 potassium also we have to add. And when we are adding 2 potassium, there will also be potassium sulfate. So it is ultimately K2SO4. So see, it is K2SO4. So total number of sulfate ion is also same both side. It is 2 SO4 here, 1 SO4, that means total 3. And here we have 3H2SO4, that means 3 sulfate ion present in 3 sulfuric acid. But mostly you don't have to convert this ionic equation to the final neutral equation. It is just for an example I am showing, but that is mostly you have to balance it always in ionic form, not in the molecular, that is a neutral form. Okay, so now if we look at this problem, it is basically only one electron. That simply you can understand from this equation only, because for 2 CO2 there is involvement of 2 electrons. So when it is 1 CO2, it is basically only 1 electron. Okay, for 1 molecule of CO2. That is the question. Now this question is very interesting. In order to oxidize a mixture of 1 mole of each. So how many species there are? Total, all are iron compound, but different compounds. FeC2O4, this is ferrous oxalate. C2O4, remember it is 2 negative charge. To balance it, there will be 2 iron. So FeC2O4, that is the first species. If I break it, it is basically Fe2 plus ion and C2O4 2 negative. Another species, that is a second species, ferric oxalate. What is the difference? Now it is iron 3 plus. So as if it is 2 Fe3. I am just breaking the salt so that you can understand what are the anions and cations involved. Now the third equation, it is F simple, it is ferrous sulfate. So it is containing Fe2 plus ion and sulfate. And the fourth one, ferric sulfate. So the first two are basically salt of iron and C2O4. Only difference is Fe2 plus and 3 plus. Third and fourth, this is sulfate. So difference is, sorry, it is 2. Difference is, third one is 2 plus, that is ferrous ion. And this is ferric ion. So these are the anions involved here. Now you have taken 1 mole of each in acidic medium. Remember, in acidic medium it must be clearly mentioned, because then only you can understand what should be the fate of KMnO4. So it is asking, in acidic medium you have taken 1 mole of each of these salt. What should be the total number of moles of KMnO4? Now here we have written this equation. KMnO4 is the oxidizing agent. So when you have taken KMnO4, obviously it will be converted to Mn2 plus. That is fine. But here in the first salt, after reduction, what will be the fate that we have to write? So in presence of KMnO4, I am simply writing oxidation sign. Here Fe2 plus, that will be converted to Fe3 plus, and C2O4, that will be converted to CO2. This should be the fate after reaction to CO2 basically. Now when you are doing this, basically there should be involvement of 3 electrons, because if you balance the total positive charge Fe3 plus, to balance it there should be 3 electrons, because in the left hand side it is neutral FeC2O4, right? So C2O4 is oxidized to carbon dioxide and Fe2 plus is oxidized to Fe3 plus. Now the second equation, when it is oxidized, it is already oxidized form. So further oxidation not possible, because you cannot have Fe4 plus, that doesn't exist, right? So only C2O4 will be converted to CO2. Now when you are doing so, it is basically 6 CO2. To balance the charge, total positive charge 3 into 2 plus 6, total negative charge, here we have 3 into minus 2. But see, once oxidation is done, oxalate ion is no longer present. You have ferric ion and you have 6 CO2. Total positive charge 6 plus. That means here you have to write 6 electron to balance the charge. What about the third one? After oxidation, the fate of Fe2 plus it will be 3 plus. But there will be no change in terms of sulfate, because here it is already plus 6, highest oxidation state of sulfur. Further oxidation of sulfate is not possible. So total positive charge is 3 plus, total negative charge is 2 negative. So to balance it, you have to add only 1 electron. And the last one, there is actually no oxidation possible. It is already highest oxidation, it is already highest oxidation state of sulfur. So further oxidation not possible, no electron involvement is there. Now for Mn2 plus, we know MnO4 minus, that is converted to Mn2 plus, and in this case we know total 5 electrons are involved, right? Now when it is 5 electron involved, now look at the first equation. It is basically a lengthy question, it will take some time. The first equation, just forget about all the equations, just focus on the first equation. It is involving 3 electron and it is 5 electron. That means when you will balance these two pair of equation, one pair of equation, one is, this is one half, this is another half. What you will do, you will multiply the manganese equation with 3 and you will multiply this equation with 5. So it means what? It means 5 Fe C2O4 minus, that is basically equivalent to 3 MnO4 minus. Now the same logic if you apply for the second reaction and the other reaction also, you will see it will be 6 electron, it is 5 electron. That means it should be 5 Fe C2O4 3 minus, that is basically equivalent to 6 MnO4 minus. And for the third equation, it will be only 1 electron. That means it is 5 FeSO4, that is equivalent to MnO4 minus. Now we have taken only 1 mole. So for 5, if it is 3, for 1 mole of FeC2O4, it should be 3 by 5 MnO4. In the second case, this is for the first one, this is for the second one. For 1 mole of ferric oxalate, it should be 6 by 5 of MnO4. And in this case, it should be 1 by 5. So now you have to add 3 by 5, 6 by 5 and 1 by 5 because it is a mixture. You have taken 1 mole of this. This is already cancelled. Now for the first one, the requirement for 1 mole of FeC2O4, it is requirement of MnO4 minus is 3 by 5. So 3 by 5, 6 by 5, 1 by 5. So it is basically 10 by 5, that is 2. So correct answer is option A. Okay, so this is a lengthy question, but this is a very good question. If you solve it, your idea will be clear. So we are at the end of the session. Thank you for listening.